Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We're going to wrap up our discussion of numerical integration in this lesson, and we're going to look at some of the complications that might arise. And the first one of these is a mathematical problem where you have infinite limits. So one or both of the limits of integration is infinity or negative infinity. In this case, it is helpful to break the integral up into pieces where you've got a finite chunk, and then the other part is going to infinity. And the advantages of that is sometimes you can, if you choose the right breaking point, actually analytically integrate that. Okay. Another possibility is that you can do a change of variables that gives you finite limits of integration. Or the third possibility is that you can choose a large enough value that all of the total area under the curve for this tail end that's infinite actually goes to essentially zero. And if that happens, then okay, you're probably in pretty good shape. But this weird one, the change of variables. So this is an example of a case where you have the integral from 0 to infinity of x squared e to the minus x squared dx. And if you break this up from 0 to 1, you can integrate this portion here. Now then, let's look at this portion over here. And you'll see as we do this why we chose 1 as the breaking point there. So x squared e to the minus x squared is a problem. But 1 over x squared, if x is going to infinity, 1 over x squared will go to 0. And if you do that, you end up with this change of variables, which becomes this piece here. Okay, it's still not beautiful, but we've got something now where I'm going to 0. And Excel is fine with evaluating things at 0. So this is a help, okay, one possibility. Another complication is when you end up with multiple integrals, so figuring the area or the volume of something, or evaluating something over a surface or a volume. And so the way you do this integration-wise is you integrate the inner loop and then you integrate the outer loop, or inner integral and outer integral. And we're going to do that with the programming, but it's going to be loops that we're going to do this inside one first and then the outside one. If you have the possibility that maybe you can integrate the inner integral, but you can't do the outer one, then do that. As much hand integration as you can do, the better off you are. And then you just have to use the normal trapezoid rule or Simpson's rule for the outer integral. If that's not going to be possible, then you can build a loop inside your loop that will evaluate the outer integral. These are called nested loops. A nested loop has to be nested totally inside the other loop. So think of these like the Russian stacking dolls. They have to be totally contained inside the other one. So for instance, here I have a loop on I that goes from here to here, and I have a loop for j that is totally contained. So it starts and it stops totally inside. Now it's possible you might have the stop of both of these right next to each other or the start of both of these right next to each other, but they still have to be totally contained. Let's look at this for an example here. Now this one actually is integrable, and I'll leave it to you, but when you integrate this you get 1/2 x squared from 0 to square root of 4 minus y squared, so the x squared will get rid of the square root sign, and it ends up just being a polynomial. And when you do it, I came up with an answer of, I think, 2.7. Let's look at it in Excel. So this is the problem. Yeah, I came up with 2.7. This was my work doing it analytically. But if I wanted to do this numerically, so I've built this into a Visual Basic file, and let's look at it. It's up here. what I've done is the outer integral is y. So I start by initiating the y. So a for y and b for y come from my limits of integration. I chose to do 100 terms. This can be very slow. Even with 100, it's a little bit slow. You'll notice the computing time if you go to very large numbers on this. And then I initiate my final sum to be 0, and I calculated delta y. So I'm working with the outer integral. I'm going to now, on that outer integral, I want to have j equals 1 to n minus 1. So I'm going to still do my trapezoid rule. And ay plus j delta y is going to be the y value as I hop along there. It's important that I identify what I'm doing, because think of it as taking a slice out of your area. And so y is going to hop from -2 to 1. X is going to then vary from 0 to the square root of 4 minus y squared. So I'm choosing my y's. They're going to go all the way from the ay to by, and I've initiated those. Now then I need to, and this next chunk of code is going to evaluate my inner integral. So I've evaluated ax and bx. Now notice bx is a function of the y, but I've already defined that. So this is my limits of integration. I define delta x. It varies because bx varies. And then I initiate that sum, and I do my trapezoid rule. Okay? Then I'm going to finish up this slice, and I need to go to the next slice. So I'm going to take this slice times delta x over 2. I'm going to add 1 to my j and do for the next slice, and I do this one slice at a time. At the end then I'm going to have to do a similar thing, take my answer and times delta y over 2, and this should actually be sum last. And then I'm going to choose a place to write my answer, and if I run this, oh, maybe that shouldn't have been sum last, maybe it should have been sum. Let me look at this. Okay, yeah, that got me pretty close to the answer. Okay, so this is the double integral, so we've got the nested looping here. Now our next complication, let me pull up my PowerPoint again, is when our data, if we were having to integrate data, if the data is unequally spaced. In this case, we're just going to use the trapezoid rule, and the easiest thing to do is not to use any fancy formulas, but just simply go from 2 points and then go to the next 2 points and calculate the area of the trapezoid. It's really a lot easier. Simpson's rule is not possible without evenly spaced data, and remember you have to have an even number of divisions, but the trapezoid rule will work. So here is some data, and if you wanted to figure out the average value of a function, then you just simply are going to integrate the function from a to b and then divide by the length of that interval, so b minus a. And so here we've measured temperature at a variety of depths in a soil sample, but they didn't really do it evenly. It's just sort of randomly, it seems like. And our temperatures range from 21 to 49 degrees. Okay? And we want to know what the average value is. Well, the good news is we can borrow from our Excel code that we've used in the past. Let me bring both of these files up. And so I've moved this data into my Excel. And then I've set up a trapezoid rule for uneven data. So here what the difference is, I've started with the same code. Okay, this portion here really is the same. All I did was adjust my locations here. So it's going to start by counting the cells and putting the answer here. It's going to count from here down to a gazillion. I don't know how many I actually did, but much more than what I thought I'd ever have taken data. And then I start my sum. And now then, I don't want to start my sum by taking f sub a and f sub b and then doing twice everything in the middle. I'm just going to do simple trapezoids. But that means that I need to read in the x's and the f of x's for this entire trapezoid. So this would be for the first one, and then the next trapezoid would use the same common first point. Okay, and so what I need to do is I've got it set up so it starts here and it comes over and it is sitting with the cell right here. Let's look at the code again. So what I did next is I'm going to call that F1, then I'm going to back up one, and that's going to be X1. This is my X2, and this will be my F2. And so then it's the average of these values times the difference between these divided by 2 is my area of that trapezoid. And I'll just add these up for every possible trapezoid. So I'm doing this by hopping from cells to cells, and I'm using this relative method of doing offset. And so I'm going here, 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 and I end up here. Now this is going to be the first place for my next one. So I'll go here, 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 and I'm going to keep doing that over and over and over again. Okay? And when I run this, in fact, it gets an average value of 40.3, which appears to be right. When I did it by hand, it matches. So this automates doing a trapezoid rule whether we have even or uneven data. So this concludes our study of numerical integration. We're going to be looking at solving systems of equations and matrix techniques in future lessons. Thank you very much for your time.